Okay, great. So welcome everybody to the SFU Sports Analytics Virtual Seminar Series. This is our 16th episode. And today it's my great pleasure to have Dr. Ian Schreier, who's contributed a lot during our series with discussion and questions since the inception. And he's going to speak to us today about causal inference, mediation, and interaction. Dr. Schreier has been practicing sports medicine for over 30 years and is a past president of the Canadian Academy of Sports Medicine. He has a PhD in physiology, postdoctoral training in epidemiology, and over 280 peer-reviewed publications on topics related to the effects of exercise and sport medicine injuries, return to play decision-making, injury epidemiology, causal inference, and meta-analyses. He was the co-editor-in-chief of Review Synthesis Methods and is an editorial board member of 4 international sport medicine journals. Oops. So today in this presentation, he will review the concepts of mediation and interaction from a causal inference perspective. He'll begin with the example where treatment, the exposure, is randomized, but we want to estimate the effect of receiving a treatment, which is a mediator, on injury rather than the effect of assigning treatment. The presentation will include under-recognized examples of collider stratification bias in sport injury, differences between controlled and natural direct effects, and why model selection using machine learning may sometimes result in increased bias. And so with that, I will stop sharing my screen and ask Dr. Schreier to share his. And welcome.
Thanks, Dave. And let's do this PowerPoint. There we go. Great. So just a little bit of background. I started my career in medicine, and I practiced for a few years, and then I got bored. Medicine's a trade school, like being a plumber. And then I decided to do a PhD. I did it in physiology, which is all about causes, and we'll get to some of that later. So that may have influenced the way I am, or it may be just I was drawn to physiology because of the way I am. One of those causal questions. And I did that for a few years, and then I got bored, and I wanted to do some stuff in humans, and I wrote a grant, and they said, great grant, but you have no experience looking at humans, so sorry. So then I went and did a postdoc in epidemiology. And so I did some clinical studies, and then I had these questions, and so I'd go to statisticians and other epidemiologists, and I'd ask them questions. And I just got more and more into theory and modeling. And so I'd say a lot of my work right now is actually in research on how to do research and methods. And then most of my actual studies are collaborations with other people who are collecting data. So this is one video that Dave, you should shut off because it's from the web. And this is now my favorite video to think about causation. And you guys do a lot of sport analytics and sport performance. And so important. My reason that particular slide is so important. Dave, you can turn the recording back on for now.
Great, thanks.
Now, this is a slide not related to mediation, but it's about causation as well. And if you read the sport medicine literature, you will read that past injury is the most important risk factor for future injury. And if you go, I'll show you a video later on from the First World Congress on Sport Physiotherapy, and that was held in Bern, Switzerland. And if you go to that, you'll see some talks by people, and they repeatedly say 2 to 19 times more risk of injury after the first injury. And they say, we're not rehabbing people properly. Now, I don't know if they were rehabbing people properly, but I can tell you that the analyses on which they base those interpretations are just seriously flawed. And that was all shown in this paper that we wrote in 2011 with Gavin Hamilton as the first author. And then I did one on concussion in 2019 using the same idea. And this is the type of graph that they look at when they say that. Here, this black line is time to first injury over athlete exposures. This is actually using Cirque du Soleil data, so it's artist exposures. Then, for everybody who had a first injury, there's a time to second injury, and that's the blue line. That occurs faster. More people without injury, the survival curve drops faster, meaning more people are getting re-injured faster, earlier exposures. And then third, fourth, fifth, sixth. So we end up with this graph. And so clearly, previous injury is a super important risk factor, but this graph is non-causal. And the reason is because there are different individuals in each of these data sets. In the first data set, we have everybody, whether they were injured or not. So everybody has a time to first injury, and if you didn't get injured, you were censored at the end. Now, to get a second injury, you had to have a first injury, right? We've eliminated everybody who has not had a first injury. And in the next group, we eliminate everybody who has not had 2 injuries. So think about it. Those people who are really prone to injury are kept in the data set. And those people who are resistant to injury are kicked out of each of these data sets. So if each time I eliminate all the people who are at lowest risk of injury, then mathematically it must be that the subgroup that I keep is more at risk of injury. And we explain this with stick graphs in the Hamilton paper, and usually I spend 10 minutes going over this. Another way of thinking about this, so what all we did in this was we said, okay, let's take people with time to first, second, and third injury. So they had 3 or more injuries. We're only going to look at time to first, second, or third. And this is the same data. Only now I'm restricting a population to 3 injuries or more, and the lines superimpose. So in Cirque du Soleil artists who have very close follow-up and very good therapy, previous injury does not predict future injury. In other words, they are able to rehab them 100%. Now, whether that occurs in professional sports or in, for recreational athletes, that depends on how good your rehab is. So let's go to mediation and interaction. That was more about causal effects and understanding confounding and why we want to know about causation. So we're going to talk about what's the research question. We're going to talk about colliders and induced associations, which is the real problem, the real challenge when you don't take a causal inference perspective is you forget about this particular issue that arises when you include variables in a model. Then we'll talk about mediation, and when we talk about mediation and interaction, there's actually people say, oh, I want the direct effect and indirect effect. There are many different types of indirect and direct effects. The 2 big ones are controlled direct and indirect, and natural or pure indirect and indirect effects, but there are other types as well, and we'll get through some of that. And if we have time, I'm going to show you bias amplification and the dangers of machine learning and interpreting when you use machine learning, interpreting that in terms of causal effects. It is great for prediction, but it has serious challenges with causal inference. And it's not that it's bad, it actually uses the same principles that standard epidemiology does, but standard epidemiology has serious problems when it tries to interpret causal effects. So let's talk about the research question, and we're going to take a randomized trial, and our question is, does treatment Z reduce mortality? Now, results are data plus assumptions, and so we have to look at assumptions and definitions here. So here we just say, hey, I'm going to randomize people, and depending if I randomize you to one group, you're going to be more likely to be assigned, you're going to be assigned treatment. I randomize you to another group, you're assigned control. If I assign you treatment, you're likely to take treatment. And if you take treatment, that might affect your outcome. So Tim Noakes had a saying once where he said, the perfect study exists only in the minds of those who do no research. The bottom line is, I assign people to treatment, but they don't always take it. Why? Because there's other reasons that some people, that treatment, it takes too long, and so I don't want to take it. Now, if the reasons that people don't take, if the causes of adhering to the treatment I assign are also causes of the outcome, I now have a confounder of the treatment received outcome relationship. And that's important. So a confounder is a common cause of 2 variables. So now what does that mean? Well, our question was, does treatment Z reduce mortality? Treatment Z. The intention to treat measure, which is what is the recommended thing by the FDA and most clinical trialists, the ITT measures the effect of treatment assignment. That's assigned treatment. But that wasn't the question. The question doesn't say, does assigning treatment Z reduce mortality? It says, does treatment Z reduce mortality? Now, the reason that they do this is that regulatory agencies want to avoid overestimation of the effect. So they go versus placebo. And so if the methods to actually assess the effect of treatment rather than assigning treatment, back in the day, 20 years ago, 30 years ago, those methods were not clear. Now we have much better methods, and those come under the rubric of causal inference. Most people want to know whether the treatment works, not whether assigning treatment as a patient. So are we actually protecting the public by using ITT? Well, let's see. Here, in this toy example, we're going to say that these two treatments are equally effective when taken. So we have usual rehab, which is 100% effective when taken, but only 50% of the people adhere to it because it takes 30 minutes to do. And then we have a quick rehab program that's 100% effective when taken, and everybody does it because it's only 10 minutes. Now, what are going to be our results? In the government, they're going to take an intention to treat approach. And in the intention to treat approach, our novel treatment is twice as effective than usual care. So the government's going to say, quick rehab is a much better treatment and everybody should do it. Now I'm going to ask you as a patient. The novel treatment is extremely expensive. The quick rehab. They're using some stuff, but it's very expensive. Yes, 100%. So you're a patient and you don't have money. Or if you went and bought the quick rehab, it would really put you out. But you know that if you took the usual rehab and you followed it, you would be just as effective. Which one are you going to do? Well, you're going to look at your overall life and the whole cost utility benefit, and you might end up saying usual rehab is the best treatment for you. So that's one example. Now let's use another example, because you're going to say, well, that's kind of artificial. Let's take this, where the usual treatment is not as good as, novel treatment is superior when taken. So here we have the usual rehab, which is 40% effective, but 100% will adhere to the treatment. So this doesn't work in something that's short, but you could imagine in COVID, let's say we had a shot that you could take that would cure you 40% of the time, but kill you 60% of the time. Now you have a different treatment, in this case long rehab, which is 60% effective if you take it, but only 50% can take it because of side effects. And they just can't take it. So let's look at what these numbers mean. If we take the ITT approach, the novel treatment, only 30% survive versus 40% with the usual treatment. So that's why the government will say in the ITT, the novel treatment is worse. And that's what was there for 50 years up until, let's say, recently in the 2000s. Now, if we want the actual treatment, though, I might say, well, wait, I don't get these side effects, so I'm going to take the treatment. That's the usual rehab, and now I have 40% chance of surviving instead of only 30%. So in actual fact, if you can adhere to the treatment, the usual treatment is better. So that's why we want to come to this causal inference approach about what is your question. So health policy requires that we actually, so if I'm in public health, I actually want to know the ITT. Because if I put out a public health policy like the COVID vaccine, if only 1% of the people take the treatment, then it's not going to work. I need to know the adherence. The adherence is part of the question. But from a personal perspective, as a patient, you don't care about adherence. You only care about what happens if you take the treatment or not what happens if like 30% of the other people don't take the treatment. Now, I want to caution you that what is traditionally used for this, they use per protocol analysis, where they say, I'm only going to analyze those people in the treatment group that took treatment and only those people in the control group that took control. That type of analysis, called per protocol analysis, is biased, and that is bad. And that is why the government agencies, regulatory, always used ITT, because that's all they had before. But now we have other things. We have instrumental variable analysis, and we have principal stratification. There's also something that's very closely related that's not on here, called a per protocol effect. Not per protocol analysis, but a per protocol effect. And that can be estimated with G methods. I should have put G methods in here as well. And so that's a different way at getting at these unbiased estimates of treatment received, because that's our question. These are all about treatment received. Now notice that treatment received is a mediator for assigning treatment. We have assigning treatment causes treatment received, causes the outcome. So this is in effect a mediation question. I'm asking, I assign the treatment, but I'm asking what is the effect of receiving treatment, which is not something I did. That is not the intervention. The intervention is assigning the treatment. And it's very important to think about those issues in that way. So I want to know, are there any questions up until now? Because it's very important, that research question, and this is mediation, and even in the context of a randomized trial, we have converted our randomized trial to an observational study because we did not randomize the treatment. We randomized treatment assignment. Super important. Cool. So now we're going to talk about colliders. And normally, I should tell you, it's about a half-hour talk just on this. So I'm going to shorten it. Here we have an exposure and an outcome. And we have some unmeasured variable here, U1, that causes the exposure and causes some other variable, C, that we can measure. And we have another variable, U2, that's unmeasured, which also causes this C and causes the outcome. Now, in this, if I actually looked at, this is the true data generating process right now. If you generate data, you simulate data here, the exposure E and outcome, if you just did a naive regression, outcome as it regressed on exposure, they are not associated. However, if you put C in the model, now also I'm going to tell you C is associated with the exposure. It's one of the criteria to know if something's a confounder in epidemiology and in machine learning when they code. C is associated with the outcome. It doesn't lie along any causal path, although machine learning tends to usually not think about that, but it's not an effect of exposure, it doesn't lie along any causal path. So according to traditional epidemiology, C should be included in the model. And in machine learning, because it follows traditional epidemiology and those model selection rules, it would probably include it. However, if you include C, we call it a collider because these two arrows collide, the arrowheads are colliding on it. You actually create an association between U1 and U2, and now the exposure and outcome are going to be associated non-causally. In other words, if this is the data generating process, Not including C gives you an unbiased answer. Including C gives you a biased answer. It is not what you want. And this is the biggest problem in the way people are running models at the current time. To explain that, this comes from, it actually comes from the appendix of Udaya Pearl's, sorry, I have to move my, one of the things from Zoom. It comes from Udaya Pearl's appendix in his first causality book. I don't have the second or third, but we explain it in this article we wrote, me and Robert Platt. So think about the season being spring, and in spring, your grass is growing, so you have automatic sprinklers, and sometimes it rains, and both the sprinklers and rain cause the field to be wet, and then having it wet makes it slippery, and you might fall and get injured. If you notice here, wet is a collider between sprinkler and rain. They both cause it to be wet. Whoops. If one knows the value of the collider, the parents are associated, sprinkler and rain. What does that mean? Well, if I tell you that the grass is wet and I told you it didn't rain, I'm sure that 99%, I hope 100, but 99% of you would say the sprinklers were on. How else did the field get wet? Well, some dog could have pissed on it or something. So there might have been other things that we didn't put in this graph, but clearly it is much more likely that the sprinkler is on if the field is wet and it didn't rain than if the field is wet and if the field is not wet, or if the field is wet and it did rain, you have no idea about the sprinklers. And if the field is wet and the sprinklers were on, well, you have no idea about the rain. So you notice that you end up knowing about sprinklers under one of the contexts of when it's wet, not all of them. But that one context is enough to mathematically associate these. So if you run this, you run it in a nice simulation example, you'll find the same thing. That if you say, oh, the field is wet, and then you say, I'm going to look at the association between rain and sprinkler, you'll find they are associated. For those of you who aren't convinced yet, I'm going to ask you a simple math question here. X3 and X2 cause X4. So we can say in this function, X4 is equal to X2 plus X3. I tell you X4 is 10. Can you tell me what the values of X2 and X3 are? And you can't. Could be anything. But if I tell you X2 is 7, I hope that all of you will say X3 is 3. In other words, once you know the value of X4, which is wet, or 10, knowing the value of one of the parents gives you information about the other. That's the definition of association. So in this one, if I put the collider in the statistical model, that makes U2 and U1 associated, and we put a line between them, and now we have a path from E to the outcome. And that's a non-causal association. And now your regression gives you a biased answer. And had you left C out, you would have been unbiased. So it is not true that adding variables always reduces bias and might just increase variance. That is not true. Now, the answer of what you should do depends on the true but unknown data generating process. So we draw out causal DAGs to highlight what we think the data generating process might be, and we're not sure. And if we're not sure, we should draw out and make all the different variations. And when we do all those different variations, we can then say, well, if it's this graph, then I'm okay. If it's that graph, I'm not okay. It might be that across all graphs, you can have one model selection that gives you an unbiased answer, and then you don't care which graph it is. So in this particular graph, which comes from Pearl's appendix, and all we did was add names to it, because one of the reviewers said, could you add names? So I just made these names up, and don't think that this is a true causal graph. If you actually throw in, so first I can tell you all of these variables are associated with the exposure, associated with the outcome, do not lie along the causal pathway, and satisfy all the criteria of confounders from all the standard model selections. And if you were going to do this, you could run backwards, forwards, stepwise regression. You could do all those things, and you come up with different variables that you would include in the model. But I can tell you that all you need is neuromuscular fatigue and tissue weakness. You put those two in, you get an unbiased answer. And we explain why. Pearl explains why in his book. He gives you the algorithm. We explain why, how each step works in a 6-step process, which we're not going to go through here. However, look at previous injury here in this model. Now, in this model, if this is the true data generating process, we could say that, hey, aggressive teams are more likely to have injuries, and contact sports are more likely to have injuries. So this makes sense, but previous injury is now a collider between these two variables. Therefore, these two become associated. And once you do that, you now have a biased answer. So if I put just neuromuscular fatigue and tissue weakness, I'm okay. If I now add in previous injury, my answer is biased. Now, that doesn't mean you should never include previous injury in a particular model. I'm just saying you have to look at what you think the causal relationships between the variables are in order to know if including previous injury is good or bad. You cannot know it without drawing your causal diagram. Essentially, people who don't want to draw causal diagrams are going, I'm going to put these things in, and I'm going to assume that I'm not having any colliders and I'm not creating any problems. I don't know. I can't think about the causal graph. I'm just willing to blankly assume it, stick my head in the mud. I'm an ostrich. I don't care. And that's fair if you want to take that approach. I think a better approach is to actually outline your assumptions directly. Let everybody know about them. Now, how important is this? So let's look at hamstring injuries. And this comes from a study done out of Doha in Qatar. And so they have their Aspetar Institute. And they did a study, I'm going to show you the video, but from my colleague. So they said in their data that low strength is a risk factor for first hamstring injury. So you have weak hamstrings, you're more at risk. Lots of studies showing that. And what they found is that they looked at those people with a hamstring injury who were rehabbed. And they found that those athletes with a high strength, who were stronger, were more at risk for a subsequent injury. So the opposite of the risk factor for the first hamstring injury. Let Eric, so if you can stop the thing, as I grew up in physiology, and this happened to us all, we have this great hypothesis, and then we get other results, and then we come up with a completely opposite hypothesis that is just obvious to you once you have the data. And that's exactly what Eric did here with his group. They came up with another idea that seems to make perfect sense. Now, I can argue with you on a physiological reason why I don't think that argument makes sense. But now I'm going to show you that mathematically, what the analysis he did would show this relationship, even if it's not causal. So I'm going to use a different example. There's something called the obesity paradox, which works with heart failure, but and diabetes and a bunch of things. But let me explain it to you this way. Obesity is a risk factor for diabetes, non-insulin dependent diabetes. Among diabetic patients, so if all I know is diabetes, diabetic patients who are obese do better than diabetic patients who are non-obese. But the reason is because obese patients have non-insulin dependent diabetes and non-obese patients have insulin dependent diabetes. They're younger. And so these are we actually consider them as two different diseases, and we give them two different names. In heart failure, obesity is a cause of heart failure. But amongst patients with heart failure, obese patients do better than non-obese. Why? Because the non-obese patients have heart failure for very serious reasons. They had heart attacks, they had myocarditis and viral infections, and the heart just doesn't work as well. So these are much more serious causes of heart failure, and they're also causes of death. So you're not comparing obese versus non-obese, it's not the only difference. They're actually different disease and pathologies going on. So now let's look at hamstrings. Among patients with hamstring injuries, those who had strong hamstrings had injuries for other reasons, like diabetes. So we have the obese patients get non-insulin, but those who are not obese are getting diabetes because their pancreas isn't working. In those people who have weak hamstrings, they get injuries because they're weak. In those who had strong hamstrings, they're getting injuries for other reasons, for other frailties. Maybe it's just the position. Let's compare hamstring injuries. Strong hamstrings are going to be in strikers more so than goalies. Well, strikers have to run and sprint and goalies don't. So if you look just at the strength, you might say it's the strength that's doing it when in actual fact it's the position. So this is due to collider stratification bias, and it affects every single risk factor analysis for subsequent events. And that doesn't matter if the subsequent event is an injury, or as we saw in the person, great talk on the soccer and trying to see about when you cross the field with a kick. I don't play football, so but when you do those cross kicks if that scores goals, those are subsequent goals. If it's subsequent body checks or assists, I don't care. It will affect every single one of those. So let's look at this causal diagram. We have the initial baseline preseason hamstring strength or weakness causing a hamstring injury, which causes future injuries. And we have other baseline factors such as your proprioception, the position you play, whatever, which can cause a hamstring injury, like I said, striker. And of course, if you were a striker, risk for the first, you'd be at risk for the second. Now, we also have our hamstring strength after the injury, which is not the same as hamstring strength before the injury. So variables are defined not just by the name and what you're measuring, but also the point in time. So these are two different variables in a longitudinal model. So now we have the post-injury, and of course, what Eric said, the re-injury group has greater strength. It was not only at discharge, but also at initial exam, but that doesn't matter much now. So the hamstring injury causes the hamstring weakness. The initial weakness, if I was weak before my injury, I'm more likely to be weak after my injury compared to somebody who was strong before their injury. So we have an arrow there. So where are our colliders? Well, here we have a collider, right? Hamstring weakness and hamstring injury and baseline, these three. So these two become associated now. Here we have a collider, but these two are already associated. We say hamstring weakness causes hamstring injury. So we have to add a line here to say these are joined. Now, if you follow the rules that, if you read the paper that Platt and I wrote, you can follow the rules, but essentially we now have what's called a backdoor path from hamstring weakness to second hamstring injury. And because of the math of this and the way these are set up, it is actually an inverse association, meaning hamstring weakness will appear protective for the second hamstring. So Eric can go through all of the physiological and anatomical things, and I can argue with him about those. But the bottom line is, even if that's not true, mathematically, we will have an inverse association. And it occurs because we are conditioning on people with hamstring injuries. So when you put something in a model, right, you put a variable in a model, or you restrict your population to that sample, it is the same thing. You are conditioning. You can think about that as a regression is a weighted average between the different levels. So if I did a study and I looked at men and women separately, ran a regression with sex in the model, I would get an overall average, a weighted average of men and women. And that's conditioning on sex. If I restrict the sample to just men, that is still conditioning on sex. I will get one number, but it is conditioning. And in the causal inference literature, it's the same thing. So here, there are people who never had a hamstring injury. They're no longer in our data because Eric started his whole data set were those with a hamstring injury. And so it's conditioning. So that's a very important point to count. Had Eric included the preseason, pre-injury hamstring strength or weakness, it could block this backdoor path and he would obtain an unbiased answer. If at that point he found that weakness predicted injury, then we would say that that's a causal effect, given if our causal model is accurate. Any questions for that?
Has he, have you suggested that analysis and has he run it?
Well, that's a whole other issue. He didn't publish that paper, but I don't want to get into the politics of publishing and who told me what, not on tape anyway.
Fair
So
enough.
we can talk about it after when the tape is off and I can tell you what I think, but that paper was never published.
Got it.
Okay, I think it should have been, but that's another issue. So I actually told him this like immediately after his talk. I said, don't publish the paper until you talk to me. But there were other political things going on at the same time in that group. So now let's talk about direct, indirect effects interaction. And so again, my purpose here is to expose you to some ideas, not explain all of these to you. All I want to do is make you aware so that you can read further, okay, in this type of talk. It's not to teach you all of these things. Let's think about workload causing fatigue, causing injury. And we might say, we're going to say the exposure is A. In causal inference, we use A for action, M for mediator, Y for the outcome. So we have this, and then we have some other path that A affects Y directly right there. And that would be we randomize, we receive treatment in the example I gave before in the outcome, or it could be any variable causing a mediator causing the outcome. And here we have workload causing injury above there. Now, traditionally, what people do, and for the people who are not in causal inference, only know about control, what we call control direct effects. And that's the effect of A on Y when M is fixed. So what do? We take M and we fix it to a certain level. And when we fix it to a certain level, there might be other causes of M and Y. So C here is a confounder of the M-Y relationship. Now notice, if this was true and you didn't know about it and you did your regression throwing M into the model, you're saying, oh, I'm getting an estimate for the effect of A on Y, direct effect. But that's not true if you have a confounder of the mediator outcome relationship. Why? Notice there's an arrow here from A to M. There's an arrow from C to M. M is in your model. Shit, I've got a collider that creates this backdoor path from A to C to Y. So now you've got an effect from A to Y, but that's causal if it exists. But you also have this non-causal effect from A to Y that acts through C because of this collider stratification bias. So whenever you do a mediation analysis, you throw a variable in to get a direct effect, you can only do that by assuming that there is no confounder of the M-Y relationship. And that, or else you have collider stratification bias on your control direct effect. That's why that previous part was so important for mediation interaction analysis. Now, if we say that there is no collider, no confounder of the mediator outcome relationship, then we have a direct effect. That's okay. That's in the entire population. So if I think about smoking, basically I have smoking, I don't know, some initiation program which causes people to smoke or not smoke and why. But if I put that into the public, what I'm looking at is the effect of changing A from the intervention to no intervention in the entire population, which includes people who smoke now and people who don't smoke now. If I'm trying to get people to quit smoking, why am I including an estimate that includes people who don't smoke to begin with? Doesn't make sense. But if I restrict people to smoke, now I have to be careful that I don't have any of these other common causes. So all of a sudden, this very simple question requires a lot more thought, which is why a lot of people don't want to use causal diagrams, because it takes a lot more energy. This is not the observed effect independent of M. For instance, if A interacts with M to cause Y, there is no such thing as a direct effect. The direct effect is undefined. It can, mathematically, there's a bunch of papers that show why you can't interpret that the way you think you are interpreting it. The other thing is, so this is an example of an interaction. And in this case, our CDE from regression is a weighted average of the two. But it still can't be interpreted causally for a variety of reasons that are too difficult to go through here. Now, the control direct effect, let's look at this from this perspective. We have our exposure A causing the intermediate, causing the outcome. That's there, right? Now here we have other causes of the intermediate. In these other causes, if you are doing your control direct effect, you put M in the regression, you are effectively saying nothing causes M. I have eliminated all causes of M. And that's the control direct effect. And that's fine if that's what you want, but you must interpret it that way. There's another type of causal effect called the pure or natural direct effect. Those are synonyms, by the way. Not to be confused with pure direct effect, pure indirect effect and natural indirect effect are not synonyms. It gets very confusing as you try and work through the terminology that they've done. Pure natural direct effects are synonyms. Now, in this case, what essentially you're doing is you're saying, I'm going to block the effects of the exposure on the intermediate, but I'm going to let these other things to continue to affect that intermediate. It's a different question. Now, this question becomes very important if I want to develop a new intervention. So I'm thinking, what would happen if I removed all of the nicotine and tar from cigarettes? Right? So I smoke cigarettes, which causes me to inhale chemicals, which then causes the outcome. Now, I might inhale chemicals because I'm a firefighter, because I've got pollution. I'm not touching any of those. But all I'm doing is removing the dangerous chemicals from cigarette smokes. That's what the pure natural direct effect would address. The controlled direct effect would require that you remove harmful chemicals from every single cause in life. Different questions. And so you have to decide what is your research question, and is it being answered by the controlled direct effect, or is it being answered by the pure natural direct effect? Then it gets into more complicated things about certain types of, in these causal diagrams, certain types of things are identifiable. We can get the answer. Other times it's always going to be biased. If it's always biased, there are ways to do bounds on the estimates, and they can do into very fancy things. Now, Tyler Van der Wiel wrote this paper, Four-Way Decomposition, in which he breaks down basically the atom into quarks. So we're not even into protons and neutrons here, we're into the quarks. And he says that he can break it down into what's called the control direct effect 0 when the exposure is equal to 0 to control. Then he has an interaction, which is interaction reference, which is the interaction occurs if the mediator is not caused by the exposure, and the interaction that occurs if the mediator is caused by the exposure. And then we have the pure indirect effect, which is the causal effect of the exposure causing the mediator causing the outcome. He breaks it into these four, and then based on that, he can recombine these in different ways to get a pure direct effect and a total indirect effect. He can break it into a pure direct effect and a total direct effect. So you have a total direct effect, which is different than the total indirect effect. This is proportion eliminated. There's a bunch of different things that you could do in these compositions, but we're just recombining these quarks into different ways to create neutrons, electrons, protons, etc. The cool thing about this article is Tyler, first, I know the reviewer or the editor, one of the associate editor of the journal, and 6 months earlier, Tyler had published the three-way decomposition for mediation and interaction, and then he submitted this. And the journal said, we'll accept it, but only on the condition that you don't come out 6 months from now with a five-way decomposition. And Tyler said, no, this is it. I think there might be, but Tyler's really, he wrote this huge book on interaction mediation. He is the guru. When outcome causes exposure, so in recurrent events like injury or in goals and assists, you could think that we have some confounder causing our activity loads, and activity 4 weeks ago affects activity now, we're tapering, and then we get injured. Now, if I'm injured, I'm going to change my activity load, but that might also affect some confounders. And so now we have the outcome causing confounders and causing the exposure in this longitudinal path. Once you have this, forget about regression. You cannot use regression to get an unbiased estimate here. You must use G methods. Otherwise, you're stuck. Some people think you can use instrumental variables. It's a debatable issue at this point. So once you have this type of thing, which we have in longitudinal, recurrent, and injury analysis all the time, we can't do it with standard regression. We know we're going to get biased answers. Sometimes we're willing to make certain assumptions. We do it, we don't do it. But really, this is super important. If you have this type of data, read up on G methods. Now, I'm going to skip over this separable effects. It's something else. And I'm going to show you in the last 2 minutes bias amplification. So an instrumental variable is something that affects the exposure but does not affect the outcome except through exposure. A constrained instrumental variable is similar. It reduces the variance of exposure but not of the outcome. So if we look at this, we have coach and genetics in our statistical model. And now I want to look at team motivation. If I look at that, team motivation here will reduce my variance of warm-up exercises because it's a direct cause. But it has no path to outcome here. Now, I don't have previous injury in the model, I have these. So these block any association between team motivation aggression and outcome. You can run this mathematically, you'll get the same thing. But this will affect exercises. So that's a constrained instrumental variable. I'm now adding a variable in the model. Now I can tell you in this particular example, I have an unmeasured confounder. I have an unmeasured confounder here of fitness level. Fitness level causes warm-up exercises and it causes injury outcome. So I'm going to have a biased answer because I don't have fitness level in the model. But if I add motivation and aggression, I'm going to get worse bias. Worse. Now here's the proof. This comes from Tyrell Stokes' work, who's a PhD student in stats that I'm co-supervising. Russ Steele's a statistician. I don't understand the math, but I get the concepts. This is using a little trick, and I don't want to go through it, but essentially a little trick for the regression. This is a multiple regression plot, but you can do this by plotting residuals, and it's essentially the same thing. This black line shows you what the true association is between the exposure A and Y. This red line, these are all the observed points, the red, and the red line shows you the regression line through them, and we see that it's biased. It doesn't match up with the black line. Now, when we include a constrained instrumental variable that explains the variance in A, notice here that the A range here is much narrower than the A range here, which is what we said before, because we're explaining the variance in A. So we shrink its range. But A explains here it explains a little bit of variance in Y. Here this point goes above. Here these things are a little bit lower, but explains much less variance in Y than A. So what happens if we shrink the x-axis but not the y, the slope goes up, we have more bias. That is graphically what's happening in bias amplification. Now, here's our example. We have fitness level causing warm-up. So here's our confounder. This is our unmeasured confounder of exposure and injury. And then we have our team motivation here. We have coach philosophy there. We're going to condition on coach philosophy. That's okay. And then in the fitness level, we have this thing here. So what's happening here now? We are explaining, in this one, it's even In this case, we're not even a constrained instrumental variable. It's a more complicated example. In traditional epidemiology, we would include coach philosophy because it looks like it's a confounder of injury and warm-up exercises, and it is. So here's the example that Tyrell did. If we use the traditional approach, y as a function of a plus this instrumental variable coach, we're going to say, in this case, it's even a confounder, but we're going to end up with this. So we're biased because the truth is over here. Here we have the whole model with U and the IV and A, and we have that. Okay. Here we're actually got the opposite effect. Our estimate's completely off. If we use artificial intelligence, it also decides to put the variable in the model, and we're still biased. If we use model selection understanding bias amplification, which I have to tell you, even in causal inference, this is not something people would do at the point. This is why Tyrell's paper is going to be so important. We get an answer that's much closer to the truth. Now, it's still biased. We haven't removed, we can't remove the unmeasured confounding bias, but we've not amplified the bias. So this is due to unmeasured confounding, and this is because we've actually increased, we've got this bias amplification by increasing a variable. So in summary, we have to be very specific about the research question. Adding variables to a statistical model can induce associations and create bias. And then we have these different types of direct and indirect effects. And standard model selection techniques may not work when there's unmeasured confounding for a variety of reasons. So I took way more time than I wanted to, and I'm over. So, but I'm willing to stay for questions for sure.
Great stuff. Great talk, Ian. Thanks so much for that. Yeah, so I'll open the floor to questions. I think, yeah, I mean, I think that was a, you know, so Tim Swartz, who had to leave, unfortunately, he said he really enjoyed it and has, you know, I think for several of us, the concepts are, you know, quite new. And so I know you've got a lot of papers on this topic, but if, you know, maybe if you could suggest to the group some topics, and maybe we can suggest a list of readings offline to forward, because I think, you know, especially in sports analytics, especially for the younger folks in the crowd, you know, that people getting into data science, I mean, you know, we're handed a data set, here's what the outcome is, can you fit a model, right? And you've got a bunch of predictors, and, you know, very little thought may go into what, you know, having those predictors in the model and what their effects may be, and the biases that can result. So I think, you know, this is of absolute fundamental importance to understand. And I'll actually, Tom Logan is still on the call, and I'd love to hear from him. He's one of our, and Alex LeBlanc is here as well. These are stats profs, and so I'd be keen to hear, you know, to what extent we teach causality and related concepts in our statistics curricula. So maybe they could chime in on that. But otherwise, yeah, please, floor is open, and you know, now's a great opportunity to discover more of these concepts. So maybe I'll start. Can you give us a brief overview of G methods? So how do you solve a problem when you've got these multiple, you know, cyclic, you know, interacting variables?
All right, so G methods, very quickly, they're basically simulation-based methods for the most part. There are sometimes you can use it just with straight probability theorems and stuff, but I don't actually, I mean, I just use statisticians. You'll never see a paper of mine with quantitative analysis that does not have a statistician, even if it appears simple, because I don't care how many times you do stats, there's just things we don't know, and you don't know what you don't know. I do want to say, in terms of, you know, when people ask questions like the regression model, you have to decide if you are trying to be a predictive question or a causal question. And you can think of that as, do I want to be able to predict what's going to happen if the universe does not change? So prediction models are, I want to be able to predict what's going to happen if nothing changes in the world. And that's important in medicine. Somebody comes to you with cancer and they say, I want to know how long I have to live if I don't have treatment. That's just a straight prediction question. Machine learning is great for that. It's great for image recognition. That's a predictive question. How do I predict where the lips are going to be in the eye, that type of thing? But most people in sport analytics, when they're doing it, I want to know which are the contexts that I score the most, because now I'm going to change. Now I'm entering into that context, but I'm going to do something different so that I could mimic the thing where I score a lot. But that's not the same as a predictive question. That's a causal question. What will happen in this context if I switch from doing this action to that action? That's causal. And so if that's the issue, you need to look at causal inference. But if it's straight prediction, for instance, for therapists, they want to know how many injuries are they likely to have every year, because I have to know how much tape to buy and braces to buy. Those are predictive questions. So that's a super important distinction that some people have a lot of trouble in between, distinguishing them.
Mm-hmm. Great, thanks. Other questions?
I have a question, Dave.
Yep,
This is
please. Go ahead.
Thank you for the talk. It was pretty interesting. I have a question just like on your last point where you're talking about like prediction versus causal, right? So when for example, if we're doing a prediction model, we look at variables and we see how variables are also like, what do you call it? Like they're related to each other, right? Mm-hmm. So is this the same thing? Like here, I'm just trying to simplify it for myself. Is like when we're talking about causation and looking at all these different variables and how they interact with each other, is it kind of the same thing? Is that you're eliminating variables that might be like correlate, like I know correlation does not cause causation, but is it the same thing? Like are we talking about, hey, if two variables are very correlated, I'm gonna eliminate it, and this method is a different way but for causation?
Not exactly. What you're really talking about is multicollinearity, I think.
Yeah.
So that's just a question of variance. So multicollinearity, if you do it, you end up, your variance goes up. So your confidence intervals are going to be very wide. So you're trying to avoid that problem, okay? In certain types of multicollinearity, you can't tell which variable you should use. And so there are certain tricks and things that you can do. But this is not just the problem of variance. This is, you are now going to get the wrong answer. So in multicollinearity, you could put either variable in and you're okay. You could put both variables in and you're unbiased, you're just large variance. Here, you go from having a correct answer to an incorrect answer. And so the idea of no association, like the association is not causation, kills us. So that would be a more basic talk on why that's a problem. But in the causal diagrams, I can show you graphs where even in the way you think in traditional, the way science is, of whether or not you should include a confounder, it is hidden that all of the logic actually is about causation. And I can prove that to you. So maybe, Dave, I can give another more basic talk on that. But it's just model selection. And if A causes B, and you'll see it in, I'll send you some papers and you can read about it there, but it's a different thing than multicollinearity.
Okay, perfect. Thank you.
Okay, sorry.
It's okay.
Dr. Schreier, thanks for your talk. Just quickly, as we're going through the building of that causal model that you showed, my mind immediately went to the idea, like, I think we can often develop a model, but so many of the potential variables are within the model we either don't have or we aren't going to be collecting. Yeah, any thoughts on that? Or like, I'm trying to wrap my head around that piece a little bit, that do we ever really have enough variables or a way to collect them to really answer this true case of causation? And I'm thinking specifically in the land of like sport injury epidemiology.
Right. So one is, there's a couple of things in the way you said that. We have to decide what the research question is. If the research question is, I'm interested in what would happen if I changed everybody from A equals 0 to A equals 1, from exposure to non-exposure, that's your research question. And what the causal diagram does is tell you whether you can answer that question. If you don't draw the causal diagram, you have no idea if you can answer it. So that's number one, the importance. Number two, the variables that you have to put in the causal diagram are the variables that are important from the true data generating process. It has nothing to do with whether you can measure them or not. You have to include them if they are important from the causal diagram perspective. And the causal diagram perspective requires that you have any common cause of exposure and outcome. That's what defines a causal diagram essentially. You have an exposure and outcome, and you include on that diagram any variables that are a cause of both exposure and outcome. If you have that, you now have a causal diagram, okay? Now, if you go into trying to break it down into direct and indirect effects, now you need any variable that is a common cause of mediator and outcome. Otherwise, you can't do it. Now you can have multiple, because if I put a common cause of exposure and outcome in my thing, obviously there are other variables that lie along those paths. There's no direct thing, so there's paths. Whether you include those other variables or not depends on, your question and what you have. The reason, so the key is, so if I go back to here, this one, this is the key in this graph. I threw all these in, but I told you that once I have this diagram, I know I only have to measure neuromuscular fatigue and tissue weakness. I don't have to measure anything else. If this is the correct causal diagram, I've now actually made it easier for me to answer my question. Because other people are going to say, oh, well, pregrain proprioception is associated with both, therefore I have to keep it. But I've just told you, no, I don't. So I can actually reduce the variables that I measure. Now, if I do have measures of all of these, which one do I include? Well, it turns out mathematically you're best off including the variables that are most proximal to the outcome in terms of reducing your variance. It's kind of like disease outcome scores work better than propensity scores, for those of you who know the difference between that. But there are philosophical reasons to use propensity scores, so we play with these different things. It's not always one component, right? We got lots of dimensions to this, and then we have to pick which one. So we think about this causal diagram. Now, what you said we can't measure them all or know them all. That's true. Sometimes we might say, well, I'm not sure if connective tissue disorder really causes neuromuscular fatigue. So in that case, I'm going to draw two causal diagrams. I'm going to draw one with this arrow and one without the arrow. Now, if I do that and my sufficient causal sets to look at this are the same, then I don't have to worry. So I don't have this here. You know what? I'm going to stop sharing and then share again. So hold on again. I'm going to just share it to my desktop. Can you guys see my desktop now?
Yep.
Yes? Yep. Okay. So I'm just going to type in here Daggity. Okay. So it's on the web. Here's a model. Okay. Hold on. I have to move you guys over here just so I can see, because it's actually, otherwise I can't see what I'm doing. Now, I like this program. This is by Johannes Texter. I'm just going to call up, he used the example we used in our paper. So this is the exact same graph I showed you before. So if you look up here, if I want to know the total effect of warm-up on my outcome injury, here he tells you, well, you know what? All you have to do is condition on coach and fitness level, or coach and pre-game proprioception, or connective tissue disorder and neuromuscular fatigue. So it gives you all of those things. And if I throw in here and I'm going to say, you know what, I want to adjust for previous injury, I can do that. And now notice here, these all change and I have previous injury included, but the sets change. And if you know about instrumental effects, I'm just going to remove this previous injury. Now I can do coach is an instrumental variable. I can do an instrumental variable analysis using coach if I also condition on neuromuscular fatigue and tissue weakness. But it's now an instrumental variable analysis and not a regression analysis. There are testable implications here. This stuff here allows you to save the code. So if I, for instance, I just highlighted all that, I'll remove it. And hold on, I got to get rid of this thing. I'm going to update the DAG. There's no DAG. But now, if I just go back in here, so you could save that to a text file, and then you just copy and paste it again, go update DAG, and it's back. So it allows you to, and then there's other things over here. There's more graphs, so, and it's very nice. It's also, he's also the author of the R package called Daggity, and that gives you some other features. They're complementary. They don't, you know, they do some of the same things, but they also do each do their own different things. So that's the way I would sort of take your question of, oh, I've got all these variables and what do I do? He makes it easy for you. And if you don't understand why, sometimes this will say that you can't actually measure the effect. And sometimes it's easy to understand why, sometimes not, but it helps you that way too.
Fantastic. Thank you, Dr.
Yeah, this doesn't deal with bias amplification, I can tell you that. Okay, that's relatively new. He understands it, but it's just not incorporated because this is about whether there's bias or not, and not the magnitude of the bias.
Right. All right. Well, it's good. So, okay. So I will ask you for a reading list that I'll distribute to the sports analytics list afterwards, because I think, you know, there's a lot of interest and a lot of, you know, we don't, to my understanding, based on some offline communications, like we don't have these in our curricula in several cases. Are you aware, or if you do include this into, you know, an advanced undergraduate or graduate curriculum, I mean, what are some of the central readings and concepts, and like how best to do this? Because this is obviously, you know, for us, like pretty, well, for me anyway, mind blowing and, you know, quite advanced, and really has to, you know, it will change the nature of the way we do research, I think.
Right.
So, you know, where do we go from, you know, from here?
Okay, so there are two things that I would say. I just typed in Hernan causal inference. So Miguel Hernan is really the best knowledge translator I've ever seen in anything. He's just super clear, and I mean, he also, it's not just, he also is brilliant other side as biostatistics epidemiologist, but the knowledge translation is just, he's really the best in the world I've ever seen. So him and Jamie Robbins wrote this book. It's online for free. So we can do that. And here's the causal inference book. I would start there as one thing. For those who know they want to get into it, read the book, start in chapter 1, in section 1. The entire first section has no statistics. Remember, statistics are about making inferences from a sample to a population. All they do is start with a population, and they go with, how do you think about causation and causality? And so because we're starting with populations, your math level doesn't even have to be high. Then he goes into inverse probability weighting later and the math of it. And then later on in the third section, they get into the G methods and G estimation and the more complicated stuff. And in the book, it's really nice because they've got these parts which they call technical points and fine points, and they're in small print. And you can read the whole book without ever reading one of those, and you'll understand all the major concepts. But if you are into the more detailed, then that's okay too. Now, for those of you who don't want to do that, who don't want to read the book or don't want to start there, he has a do you guys know about edX? Okay, yeah. So edX is like Coursera. Miguel has a great course called Causal Diagrams, Draw Your Assumptions Before Conclusions. Great title. Like I told you, he's a great knowledge translator, right?
And so that's great. Wow.
Yeah, and so he works through all of the elementary concepts there. And oh, well, starts February. There's a session available, but you can actually just do it yourself without running it along and sort of go through. And he breaks it down, nice, beautiful things. So that's without the book. Those of you who are visual learners, maybe start with that, then pick up the book. If you just like learning on your own at your own pace, the book is really, really super. So that would be where I would start. I'll send a couple of articles, like the article that Robert and I wrote and that Miguel and Steve Cole wrote about the direct indirect effects. So I can send you some of those simple articles, but these are really the best two starting points for anybody.
That's great. Awesome. So are there any final questions or comments before I stop the recording? Okay, so I think we're probably good on the formal part of the presentation. So I'm going to thank you very much again. I mean, it was, every time you pop in, chime in with questions, it's always you always ask some stingers. So it's finally great to hear your framework of that your thought process and the conceptual framework that you're bringing to our talks, and to understanding and to really probing better the methods that we're using. So I really want to just thank you again for this excellent talk. And yeah, I'll definitely be talking to you offline about potential future talks if you're interested in contributing more. And thanks very much also for all the resources that we can look to expand our knowledge in this area. Thanks again.
Great, thank you.